All right, we're back. We are on page 5 of note 7 of Calc AB. It's all about related rates. We've done some triangle problems. We've done some cone problems. We found out cone problems are really basically triangle problems where you have to eliminate a variable. Usually you eliminate the radius because usually you're more interested in the height and the volume, but like who knows. What we saw was basically what I just said. When you're dealing with volume, this formula in particular, well, I mean, like any formula that has more than one seemingly independent variable, what you're going to have to do is get rid of one of them. But the problem will provide you with enough geometric information or just explicitly given information to do that. So here's what I would say is my strategy for dealing with what I call an abundance of variables, meaning one or more additional variables than you need. So I'll write down every formula, like every formula that the problem suggests, including like if they give me a cone, I write down the volume, things like that. Pythagorean theorem, always there. Note the variables for which you know rates of change. So you will be told some rates of change, guaranteed. Write those down. Write down the variable that you want the rate of change of, right? So are you trying to find dv dt, dh dt, dr dt? What are you trying to find? Write down the ones that you know, write down the ones that you're trying to find. Any variable that you don't know the rate of and you don't want the rate of, find a way to get rid of. And you'll do that by using like a simple equation, do a substitution, something like that. Something will be there. So that's what we've been doing so far. The next bunch of problems just going to be about circles, right? So circles do show up, squares show up, like basically anything could change with respect to time. So later on, when you know more calculus, you'll have like cars that are traveling and like the distance is a function of time and the like gas consumption is a function of distance, and you'll like have related rates that way. But for now, let's take a look at this circle problem. So a computer draws a circle that begins as a point and expands over time. Okay, I can imagine that. The instant when the circle has an area of 12 pi centimeters squared, the radius is increasing. All right, so what do we know? We know, whoa, we are given that area is going to be 12 pi at the instant we're interested in. Not always, but at some instance. So we know that area, let me just write down the area of a circle, right? Area of a circle, pi r squared. All right, so the instant we're interested in, area is going to be 12 pi, which if that's pi r squared, then the radius is the square root of 12. Divide by pi, square root. So the radius that we're interested in will be the square root of 12. At that exact moment, the rate of change of the radius is increasing. So that's dr dt is going to be 4/3 and then centimeters per second. So I'm going to write that down. Usually I don't, and it's a bad habit. I should have better habits. So we want to find the rate of change at which the area, so dA dt, is changing at this instant. So we're looking for dA dt, indicate units of measure. That's pretty much always going to be there. You should do it even if you're not asked. So I feel like I should also, because I highlighted the one thing, I feel like I should highlight this. The radius is increasing at a rate. So I just felt like I should. All right, let's find dA dt. So we're going to do d dt of A is d dt of pi r squared. All right, so this side is just dA dt. And this will be 2 pi r, but then r is a function of t, so a chain rule situation gives us a dr dt. And then what can we sub for? So we know that we need to sub for r, but we know that r is going to be this. Oh, man. We know that we need to sub for dr dt, but dr dt is also given. So this is a pretty straightforward problem. We just have to set it up and then make our substitution. So dA dt, I don't know why I'm doing this all out of order. Well, not out of order, but like, why is it out? Why are the equal signs not lined up? Like, I feel like that's going to bother some people. It's bothering me a little bit. Root 12 and then 4/3. So what do we get here? I'm going to say it's 8 pi root 12 over 3. And then what are our units? So area should be centimeters squared, which is given in the problem. It says the area is 12 pi centimeters squared. centimeters squared per second. So centimeters squared per second. And there we go. So it seems like I like to highlight these days. I'm going to say that that is my final answer for this problem. All right, let's take a look at the next one. This is not a circle problem. An isosceles right triangle has legs with length s. I feel like it's asking me to draw that, so let's draw that. There's one leg, there's another leg, and then, you know, you do your best. That does not look isosceles, but this is that, and this is S, and this is S, and it's also a right triangle. Okay, at the instant when S is radical 45, so pretty explicitly given. So S will be radical 45 centimeters. I wonder why that's not simplified. 3 root 5, anybody? The area of the triangle is increasing. So that'll be dA dt is going to be 15 centimeters squared per second. Okay. At what rate is the hypotenuse? Okay, so I'm going to say that the hypotenuse is just S root 2. Now I'm going to call it H. I'll call it H. And H is S root 2, but like, I don't know how I want to approach this yet. At what rate is the length of the hypotenuse increasing at that instant? Okay, so what do I know? I do know, and I actually said it because I was going to just make it S root 2. It's S root 2. I know that H is actually just S root 2. So I actually think what I'm going to do in this problem is find ds dt and then use that. But I'm looking for, I want dH dt. So this is kind of interesting because the formula that is sort of suggested doesn't really use H, right? Because we know area, and area is 1/2 base times height. So the area is 1/2, the base is S and the height is S, so 1/2 S squared. So I can find the derivative of that with respect to time. So let's do that. That'll be dA dt is equal to S. So it's 1/2 times 2S ds dt, which just becomes S ds dt because 1/2 and 2. Okay. And then I know, so I need sub for some things, right? I need S, but I have S. And then I need, I'm going to solve for ds dt. So I need dA dt, but I also have dA dt. So I kind of know everything that I need here. So I'm going to say it's 15 is equal to, should I make it 3 root 5? I don't really know. Yeah, I'm going to do that. 3 root 5 ds dt. So this is the same as 3 root 5, just in case. So ds dt is going to be 15 over 3 root 5, which is 5 over root 5, which is actually just root 5. And maybe that's not as clear to everyone as it could be. So I'm going to say it's 15 over 3 root 5 equals 5 over root 5, which I've multiplied the top and the bottom by root 5, or just think of the top as root 5 squared. Either way, you get just root 5. So we're good there, hopefully. Now, I also know that this is true. And so once I know this, I'm going to take my derivative and say dH dt is root 2 ds dt. And I know what S is. No, I don't. I know what ds dt, well, I also know what S is, but I don't need that here. I need to solve for dH dt, so sub for ds dt. And ds dt is this. So I'm going to sub that. I just realized I used like my final highlighter color on that. So root 2 times root 5. So dH dt is root 10 what per what. So H is a linear measure, so it should have units that are, so we have centimeters, and then what is our time? Our time is per second. So it's going to be centimeters per second. So cm per second. And then what should I highlight that with? I'm going to highlight it with, I use a lot of colors on this one. This color. Final answer, dH dt, right there. So I don't think my work is like super neat on this one. So what I'm going to do is actually cheat a little bit here. And I'm gonna move this work over here so it looks like I worked kind of from left to right, because that's probably what you should do. And I apologize if you were like taking notes at the time and you wanted a perfect replica and you're missing out on it now. But anyway, that's the whole page. So we had a circle problem. Just relax and do your circle thing, right? Circles have an area, they have a circumference. It's gonna be an area or a circumference type problem, and you just do it. And then we had this one where we had to like get into the geometry a little bit, but special right triangles, there's nothing terrible about them. You just gotta know what you're doing. So I'm gonna call it a day on this, and I'll come back in the next video and do the next page of the note. So I will see you there.